All right, open up your book to section 7-5. We're on page 365 in your book. And the title of this section is Parametric Functions. And the objective is, given equations of a parametric function, we want to be able to plot the graph and make conclusions about the geometric figure that results. We've already dealt a little bit with that in the first part of this section. Hopefully you got down what the equation of that parametric equation for an ellipse looks like. You can recognize not only the graph and be able to write the equation, but vice versa, given the equation, be able to come up with what the sketch must look like. All right. In addition to working with ellipses in this particular section, we also want to be able to work with straight lines. And the book won't ask you to come up with the equations of straight lines, but I am going to ask you to do that. So I'm going to show you how you come up with the equations of straight lines, and then expect that those show up in your sketches as well. So for a parametric equation, this is the equation of a line. We know what the equation of a line looks like if we're in function mode or in Cartesian, y equals mx plus b. But if you switch over to parametric, this is what you've got to do. If you want to sketch a line from the point AB to the point CD, I guess technically we're talking about a line segment, from the point AB to the point CD. And we're also talking about working in the domain from 0 to 360 for our values of t. If you change that, then obviously that changes this equation here slightly. But here's what you end up with. If you graph x is equal to c minus a, that's the difference in the x values there, on those 2 points, c minus a divided by 360. If you multiply that by t, your parameter t, and then add on the a value, the first point, the x value of that first point, you end up with the equation of a straight line that starts out at x equals a and ends at x equals c. For y, very similar equation, but it's in terms of the y values though. So you take d minus b, that's the difference in the y values from those 2 points, d minus b, and divide it by 360. You multiply that by your parameter t, and then add on your starting point there of b. That will give you the y values for your point that go, or for your line that goes from y equals b to y equals d. Now to see why that's the case, we kind of did this with the examples that we saw in the first part of this section. But if you're trying to, well, let's look at the equation for x here. If you're trying to come up with an equation that will give you values from a to c, but you're starting with values of t that go from 0 to 360. What I'm trying to do is figure out what do I have to do with that value of t in order to end up with, instead of values from 0 to 360, instead to go from a to c. So to do that, if you take this equation, or this inequality, and the first thing we're going to do is divide through by 360 degrees. So divide everything by 360. 0 divided by 360 is still 0. T divided by 360 is 1 over 360 times t. I'll write it that way. And then 360 divided by 360, of course, is 1. Because technically we lose the degree here when we divide by degrees. All right, now let's multiply by the difference in those x values. So we're going from x equals a to x equals c. So take c minus a and multiply that through. So of course 0 times anything is still 0. When I multiply by c minus a, this constant out front, I'll just multiply it by the c minus a. So I'll put that in the numerator, c minus a over 360 times your t. And then when I multiply 1 times c minus a, I of course get c minus a. So we've multiplied each of the terms in there by c minus a. And the last thing is I want to start this out at a. I don't want to start out at 0, so I have to add on the starting point. I want to start out here at a. So add a to everything. So 0 plus a, of course, is a. C minus a over 360 times t. When I add a on, I'll just put that at the end. And finally, when I take c minus a and add a to that, I end up with just c. The a's cancel each other out. And there we go. We have that if I calculate what I've got here in the middle, c minus a over 360 times t plus a, I'm guaranteed that I'll get values that are between a and c as a result. So that's the exact same reason that you're seeing that is that equation right there. That's where that's coming from. Again, we kind of did something similar to this when we were looking at the graphs of those ellipses the first time to just get an idea of what range we were working with. But I can do that same technique there to come up with my equations for my straight lines here, x and y. All right. Let's take a look at an example where we want to use this. So what I've got here in example number 4 is this sketch. It says the figure there shows the outlines of a cylinder. And they want you to duplicate this figure on your grapher by finding parametric equations for ellipses to represent the bases, and then drawing lines to represent the walls. And we're going to actually come up with the equations for all 4 of these. When I say all 4 of these, that's because we got 4 things we're going to sketch here. We're going to sketch that top line that you see and that bottom line that you see just by using the equations we just wrote down. And then you've got a semi-ellipse. We're only going to sketch the solid line, so we'll sketch this semi-ellipse over on the left side and then this full ellipse over here on the right side. So that's what we want to come up with, is what are the equations of those things there. All right, so let's start out with the full ellipse, because we've done some work with that already, so hopefully we are most comfortable with that. We know the equation of it. All we need to know is some key points here to work with. I need to know where the center of the ellipse is at, and I need to know the x radius and the y radius. So this center right here, it looks like, is that what, 5, 10? That's 11, it looks like right here, and 5. So 11, 5 is the center of it. And as far as my radii are concerned, well, it looks like your x radius is a little bit more than 1. Maybe we'd call that 1 1/4. I'll do that, 1.25. If you said it was something slightly different, that's probably fine, but I'm going to use 1.25 here. That's our x radius. And then for our y radius, 1, 2, 3, 4, it looks like is the y radius. So this is our y radius. This is our x radius. So there we go. I've got all the pieces I need in order to come up with this equation now. So for my full ellipse, maybe I'll call this x1 and y1 just because we're going to have several equations here to work with. So x1, y1. So x1 is just going to be h, which is the 11. I guess I'll write these down together. 11, 5 is the hk. Plus, and then I can do my dilation factors. My x radius is 1.25, and my y radius we said was 4. We multiply by cosine for x and by sine for our y. There we go. There's our equation of the full ellipse. Again, hopefully we recall that formula from the first part of this section, but that was the equation we had. All right, so now let's deal with this semi-ellipse that we have over here on the left. And again, the semi-ellipse, I'm only interested in sketching the solid part, so that's this left half of that ellipse is what I'm trying to sketch. And again, I need to know the location of a few things here. The x radius, first of all, the center is at 2, 5 again. The radius, I think the radii are the same between these two actually. So I think that's 1.25 and this is 4 again. So those are the same. Sometimes they turn out to be the same, like this cylinder. I guess they should be the same. Other times they might be different if you're looking at a frustum or a cone or whatever it might be. Then you might end up with something that's different. Okay, so now for our semi-ellipse. Now this will have to deal a little bit with that value t. We'll deal with that at the very end though for each of these. Let's call this x2 and y2. Again, the center is at 2, 5, so that's our h and our k. And we've got our x and y radii. Our x radius is 1.25, our y radius was 4, and we multiply our x's by cosine. And I'm going to wait to plug in something inside of those parentheses. It's not going to be just t. I've got to do something with that in order to get just the semi-ellipse. And then for y, it's, of course, sine. Let's deal with what's going to go in those parentheses. If I just put t, I know that I'm going to end up with a full ellipse, which I'm not trying to get. I'm trying to only get the semi-ellipse. And that's because t goes from 0 to 360. And kind of what we're going to do here is the same thing we just saw on the previous slide there to understand why those equations we saw there were the equations of your straight lines. What I want to do is end up with an interval here that's not 360 degrees wide here. Instead, it's only going to be half of an ellipse, so it needs to be 180 degrees wide. But more importantly, I need to know which half I'm looking for this ellipse. If you haven't paid attention when these ellipses start sketching there on your calculator, what you should notice is that they start right here. They start kind of off to the right of the center is where we start, and they go around in this direction. So this is where 0 degrees is at, and if you plugged in 0 degrees into your sine and cosine function, you'd see why that is, that the cosine is equal to 1 there, but the sine is equal to 0, which is why we end up with this starting point. Which means that this is at 90 degrees, this is at 180 degrees, this is at 270, and then we're back around to 360 at the beginning. So for us, we want an ellipse that starts out at 90 degrees and then goes around to 270. That's what we're looking for. I'm trying to come up with an equation in terms of t that's going to give me values between 90 and 270. That's what we're trying to do. So here's the technique here. The first thing that we're going to do is divide everything by 360, and you could do that slightly different for this problem, but I'm going to go through this the same way we saw in the previous slide. So if I divide everything by 360, this will be 0 is less than or equal to 1 over 360 times t, which is less than or equal to 1. So I've shrunk this down to an interval of 1 unit. And now what I'm going to do is multiply this by whatever interval I want to have. So in this case, I want to go from 90 all the way to 270. So that's the difference of those two is going to be 180 degrees. So let's multiply through by 180. So if I take and multiply 0 times 180, I get 0. If I multiply this constant times 180, I'm going to go ahead and write it as 180 over 360 for the moment. But of course, that's better known as 1/2 times t. And that's less than or equal to 180 times 1 is 180. And we're close to what we want now. I've now got something that's going from 0 to 180. But actually what I want to end up with is I want to end up with going from 90 to 270. So I have to add on my starting point. I want to start at 90. So add 90 to everything. I'll have 90 plus 0 is 90. I'll have this 180 over 360 times t plus 90. And that's less than or equal to 180 plus 90 is 270. And now I have a little formula here that tells me, I'll simplify this here in just a second, but I have a little formula here that tells me that if I calculate 180 over 360 times t plus 90, then I'm guaranteed I'm going to get values between 90 and 270. That's what I'm trying to do. Get outputs that are in that interval. Now, if you look at that equation that we've got in the middle there, that's the exact same equation that we just had on the previous slide. The 180 is actually the difference in 270 and 90. That's where that came from, divided by 360 times t plus my starting value of 90. This turns out to be the exact same equation that we have on the previous slide, but this is where it comes from. Let's write this as 1/2 t plus 90, which is less than or equal to 270. Kind of the short story of this is if you want to find an equation that, or the range to plug in there for cosine and sine, take half of the values of t, because I only want half a circle, or half an ellipse is why I'm using 1/2 there, and then add on whatever the starting point is. Where do you want to start as you're going counterclockwise around this? So in the future, we probably can do that a little bit faster. We don't need to go through all those steps, but there's what we have. 1/2 of t plus 90 degrees, 1/2 of t plus 90 degrees. Why 1/2? Because I only want a semi-ellipse. Why plus 90? Well, because I want my sketch to start up here in the top at 90 degrees. All right, 2 down, 2 to go. Let's do the top line first. I guess it doesn't matter whether you do top or bottom line. Let's do the top line next. The top line is going to follow the formula that we just had on the previous slide there, but let's write down the points that I want that top line to go between. So that top line is starting right here, which is at the point x is 2 and y is 9, it looks like. So this is 2, 9 is the location of that point. And I want to go all the way over to here, which is at 11, 9. So that's my AB and my CD. So I'm just plugging in those values into that equation, similar to what I do for my ellipse. Just know your formula and use it. So for x, let's call this x3 and y3. Maybe I'll even write over next to this that we're going from the point 2,9 to the point 11,9 is what we're trying to do. All right, so all I do is I take the difference in my x values here, so that's 11 minus 2. In fact, I'm going to write it that way just so we can see that. So it's c minus a, 11 minus 2, divided by the 360 times t, plus my starting value. I'm starting at x equals 2. And if you want to simplify that, of course you can, but there's our formula. In fact, I would suggest you at least simplify the numerator there. It's 9 over 360 times t plus 2. And for our y's, let's do the same thing. In this case, it's the difference in the y values. That's 9 minus 9 divided by 360 times t, plus your starting value, which is 9. That's what you end up with in the numerator there. 9 minus 9, that's 0. So this part of it just turns out to be 0. We end up with just 9, which should make sense to you since it's a horizontal line. The y value there is always 9. Doesn't matter where you're at in terms of t or in terms of x. It's always 9. What's the y value I'm plotting on this line? 9, 9, 9, 9. Everywhere is 9. So actually, that one I didn't have to go through so much work, but nonetheless, it still works out. The formula does. All right, let's do one last line here. We got 3 of these down. We got the bottom line to do now. And let's mark what we want here. We're now going from this point right here, which is at 2, 1, to this point right here, which is 11, 1. So there's our AB and our CD. Again, the y value here, because it's a horizontal line, is the easy part, but we'll still write our equation out here. X sub 4 and y sub 4. So again, we're going from 2, 1 to 11, 1. That's what we're trying to do. All right, so take the difference in the x values there. It's 11 minus 2 divided by 360 times t plus our starting value. Or you could write that as 9 over 360 times t plus 2. And for our y's, it's 1 minus 1. There's that 0 again showing up. Over 360 times t plus 1. Or that's better known as just 1. All right. That should give us the equation there of our cylinder that we've got sketched here. So let's grab our calculator and plug in these equations and see if, in fact, we end up with the graph that we are expecting to get. Go ahead and grab your calculator. All right, so on your calculator, again, make sure you're in the right mode. We're going to do this in degree mode, and we're doing this in radians. So go to your mode and make sure that we're doing it in degree mode and we're doing it in parametric mode. So make sure you got those 2 modes set there. And now let's go to your y equals menu and let's plug in the 4 equations that we came up with. So let's start with the full ellipse. We had 11 plus 1.25 times the cosine of t. And we had 5 plus the 4 times the sine of t. That was our equation of our full ellipse. Then for the semi-ellipse, this was centered at 2, 5. So it's 2 plus 1.25 times the cosine. Now, because I only want the semi-ellipse, we said we had to take 1/2 of t and add on the 90 degrees. So I start in the right spot. I want to start in the top of my ellipse as opposed to off to the right like we normally would start with t equals 0. And then it's going to be 5 plus 4 times the sine of the same quantity there, 1/2 or 0.5 if you want to write it that way, t plus the 90. And then finding the equations of your straight line. Again, the book is not going to ask you to do this, but I'm going to expect that you are doing this. Find the equation of the straight lines as well. So that's what we went through to find. We started with the top line there, so that was, let's write it in a simplified form, I guess. It was 9 divided by the 360 times your t, and then plus 2. And for the y's, that was really nice because it was a horizontal line, so that means your y is just 9. That's really easy. And then for the bottom line, turns out the x equation is exactly the same. It's 9 divided by the 360 times t plus 2. And for the y's, now it's got to be dropped down to y equals 1. All right, and let's make sure that we put this in a window that will show up. We're going to go from 0 to 360. All of our calculations are based on that, so it's important that you stay in that. I'm going to change my t-step to 4. You could do 4 or 5 would be decent there, but I'm going to go with 4 because that'll give me 91 points plotted. That'll be a decent sketch. And for our x-min and x-max, well, I'm going to just steal the window they gave us actually there. They went from 0 for the x's, and they went all the way out to, what, 5, 10? It looks like they went all the way out to 15, so I'm going to do that same thing. And maybe a scale, I'll leave it a scale of 1, it'll be fine. And then for our y's, they went from 0, and they all went all the way up to 10, and they left their scale at 1 for that as well. All right, let's go ahead and graph that. And very quickly there, we should see ourselves end up with a nice little cylinder. Again, we did not sketch the dashed lines. If you wanted to do that as a fifth equation, you could, and then you could change when you go to your y equals menu. You could even change over here that it's a dashed line. If you wanted to add that in there, that would be kind of cool. You don't need to do that, though. Oops. You can just simply graph the solid lines. All right, but I do want to see all the solid lines sketched there. So the full ellipse, the semi-ellipse, and then your two horizontal lines gives us that cylinder. Grab a picture of that. We'll paste it in here. That looks like a really good sketch that we ended up with. All right, and that's the end of the second half here of section 7-5.